Resistance, resistivity. Third section of the Physics C Unit 1 notes. Super, super short, just this one page, okay? So I'm going to get through it pretty quickly. The equation for resistance, okay, is R equals rho L over A, okay? You may not recognize what rho is, and I'm going to explain it here in just a minute, okay? This is the resistance of the object. R is the resistance of the object, okay? L is the length, okay? And A is what we call the cross-sectional area, okay? So the cross-sectional area is basically, if this is our resistor, right? The cross-sectional area is the area of, like, you know, if you were to slice it in half, what would be the shape there, right? For example, for a cylindrical resistor, the cross-section is a circle, okay? There it is, right? There's your circle. Okay. Now, resistivity is what rho is. Rho is resistivity. This is called rho, RHO. Okay. The units for rho are what we call ohm meters, and that is terrible. Ohm meters. Okay. Ohm meters. How exciting, right? Okay. Now, that's ohm meters. Okay. And resistivity is kind of interesting because it's like a coefficient. Okay. It's almost like a coefficient of resistance. Okay. What resistivity it depends on is the substance the resistor is made from. Okay. It's what the resistor, it's the substance that the resistor is made from. Okay. Okay, here's an example. Suppose that we connect the left side of a resistor cylinder to the positive terminal of a battery. Okay, so we set up a circuit here. We've got a battery. The wire is connected to this cylinder. Okay, it's resistive, so it acts sort of as a resistor. Okay, and we can connect a wire. So we have one wire here, one wire here. We can move this wire. Okay, back and forth. So how can we use this as a variable resistor? So I want to point something out really quickly. When you have a something like this, when the current is flowing into an object, whether it's a resistor, whether it's not a resistor or something else, right? Then what it is it's going to the current is going to flow through that object, but it's going to go immediately for the wire. It's not going to dance around in the resistor. It's going to go straight for the other lead in the circuit. So we're not going all around the cylinder trying to find it. We're literally just going straight to the other lead to get it back into the wire, right? Okay. So how can we use this as a variable resistor? Well, if this is the only length that which the current is traveling through, that's our L right here. This is our L. Okay. Now, if you know that resistance is dependent on L, okay, if we increase L, resistance goes up. If we decrease L, resistance goes down, right? So how can we use this as a variable resistor? Okay, well, if we slide this contact to the left, L is decreased. Okay, that's less L, so less resistance, okay? Or we can slide the contact to the right, which gives us more L and more resistance, okay? Okay, part B says that if, this is the symbol for a variable resistor. If you see a diagonal arrow across any circuit element, it means that you can vary it, okay? So we're going to draw a circuit with a battery, switch, variable resistor, and a light bulb, and it needs to meet these parameters. If the switch is closed, lights on. If the switch is open, lights off. Okay. If a variable resistor can act as a dimmer switch, so we can make the light bulb dimmer or brighter. Okay. So here's how we're going to draw it. Okay. It's just going to be a simple, what we call a series circuit. Okay. A series circuit means everything is all in a straight line. We'll go over that more in the future. Okay. So I'm just going to draw. Here's my battery. Okay. I'm going to draw my switch. Remember, your switch always should be drawn open so that people can see that it's a switch. Okay. And remember your dots there. Boom. Here's my light bulb. Okay. Down here. Here's my resistor. Boom. Okay. That's going to be our way. How does this work? So charges, when they leave the battery, it's almost kind of weird. When charges leave the battery, they take only at wait, they are given however much energy, right? And their goal is to not come back to the battery with any energy. Okay. So if they are leaving the battery with this many joules of energy, they need to make sure they get rid of that many joules. Okay. Now, depending on how much resistance the resistor has, is how much energy they need to be able to give to that resistor. So if the resistor is set really low, then that means that the energy it doesn't need as much energy. The charges can then spend more of their energy on the light bulb to make it brighter because they don't have to spend as much on the resistor. On the other hand, if the resistance is really high, then it's going to be that they need to save a lot more energy to get through the resistor than the light bulb. So the light bulb is not going to be very bright because it's not getting a lot of energy. Okay. So bright, for a bright light, it would need to be a low resistance. Okay. Because, so that charges flow faster and therefore deliver energy faster. Okay. All right. Okay. The final part on here is a new circuit that does the opposite. So we said that low resistance makes the light bulb brighter, but now we want low resistance makes the light bulb dimmer. Okay. How can we do that? Well, we can use the other type of circuit, which is called a parallel circuit. Okay. So if we were to do that, we would draw this. Here's my battery. Okay. Boom, boom. I meant to draw my switch here. I'll just make it a kind of a large circuit. Boom, boom. Here's my resistor. Okay. Draw that back to the battery. And then we have the light bulb in another branch. Boom. Okay. There you go. And this is a variable resistor. Okay. So when you have this now, here's what's going to happen. So when you have this is a parallel circuit. Okay. When you have a parallel circuit and you have two branches, the charges are going to gravitate towards the branch that has the least amount of resistance. I call that the path of least resistance, right? Um, the charges are going to gravitate towards whichever one has lower resistance. So, for example, if you set the resistor really low, they're going to look and see, okay, the light bulb has some resistance, but this has like very little. So I'm going to go through this resistor because it doesn't take a lot of resistance. Okay, great. Okay. Meanwhile, if you make this resistance really high, then what's going to happen is they're going to look and see, okay, well, there's a lot of resistance here, but there's not as much comparatively here. So I'm going to go through the light bulb, which means more charges are delivering energy to the light bulb. Okay. So if resistor is low, okay, charges go through R instead of bulb. Okay. If resistor is high, okay, charges go through bulb instead of R. Okay. So if the resistor here is high resistance, then the charges aren't going to want to go to it, right? Some will still go through, but the charges in general aren't really going to want to go through it. They're going to go to the bulb. You can think of it like if you're at Walmart, right? Do you want to go to a cashier who's really slow at bagging the groceries and everything, or do you want to go to a cashier who is a lot faster? You don't want to be stuck at Walmart all day, so you're naturally going to choose the one that goes faster, right? You can think of it in terms of this: high resistance versus lower resistance. Okay. All right. That's resistance and resistivity. Have fun.